Hi everybody, Dr. Waite here. Just to begin with a couple of announcements for this recorded lecture. The reason why it's put on YouTube and we're not having class today is so that you can attend the career fair. As a reminder, that goes from 12 until 5, and so I'd really encourage you to attend. I think it's going to be a great opportunity to meet employers and get the word out there so you can find maybe an internship or a job. And to give you further incentive to attend, if you post a picture of yourself at the career fair so that I can tell that you actually went, along with a picture of some sort of business cards or brochure or swag or something that you got from companies that you talked to. If you post that by Friday at 5, then I'll give you 1 bonus point on the exam. All right, so the other announcements are a reminder about homework number 7, which is due on Monday of next week before class, and then the project is due on November 17th. I'm going to, at the end of this lecture, give you some advice on how to do the project. There's kind of like some getting started details that I'll talk you through, so that's at the end of this video. And what we're going to have in the class part of it is an illustration of why you shouldn't compare internal rates of return, and some additional practice on calculating the external rate of return. So there is an in-class exercise that goes along with this, which I'll email to you, and that'll also be posted on Blackboard. So the lecture part of it was recorded in a previous semester, so there may be some incidental references to time or places that don't quite match up because it's from a previous year, but the material's the same, the in-class exercise calculations are the same from what I'll email you and what you see in the video. So I'd encourage you to actually work through it. Don't just watch the video, but pause the video as you solve these things on Excel, because if you actually get engaged and you go through the exercise and you get the practice, then that's going to be a lot more valuable to you. All right, so let me know if you've got any questions, and I'll see you back in class on the 6th of October, which is Friday.
Remember, in the last class on Friday, what we did was we took a look at a cash flow diagram, and let's just say, for instance, that we have an opportunity for investment, and we invest a certain amount of money, and then that buys us future revenues. The question is, what are you going to do with the money that you get, these annual revenues? Where are they going to be put? And so the annual profit of $50,000 per year, if you're going to be reinvesting it into the same account or into a different account that happens to pay the same rate of return, then you could know what the rate of return is by using the IRR approach, the internal rate of return. But if that's not a possibility, and if instead you're reinvesting these profits into some other account or into a different project that is generating profits at a different rate, then you have to come up with a weighted average of the rates of return, and that's what the external rate of return was. And so today we're going to look at both IRR and ERR in a little bit more detail. But this is kind of the need. This explains or kind of summarizes again why we have to have 2 different methods for developing the rate of return. So here is that visual summary of what we were doing when we were calculating the external rate of return. Remember that the method was we discounted all of the revenues to the present, all the costs to the present, compounded the revenues to the future, and so that we were aggregating all of the outflows to P, the present, aggregated all of the inflows to the future date, and then we discounted that future amount at some unknown interest rate. It's initially unknown, but we iterate and solve for lots of different I values till we find what is the I value that makes the magnitude of that revenue amount equal to the magnitude of the cost. So that was just the visual summary of what we did to calculate the external rate of return, and this is the template file that you started with in class on Friday to calculate that external rate of return, where you'd be given the external reinvestment rate. That's known, what interest rate you're going to earn When you get the profits and put them somewhere else, that external reinvestment rate is a given, but what you're trying to goal seek and find is the external rate of return. So it's a complicated method, but it enables us to more realistically predict what the rate of return is going to be based on what you're doing with the profits. So internal rate of return analysis can't be used for comparing alternatives. So not only is it limited to projects where you're reinvesting the money, but also internal rate of return can only be used for initial screening. It can't be used for selecting which alternative is best. Now, the definition of the best project is the one that yields the most profit. That's what companies are trying to do, is they're trying to maximize the amount of dollars that they're getting. And what we're going to see in this in-class exercise that we start with is that sometimes the internal rate of return that's the highest isn't for the project that yields the most profit. And so that's why we can't use the internal rate of return for picking which alternative is best. Just because one particular project has the highest IRR doesn't mean you should choose that project. The project you should choose is the one that yields the highest profit. So using the IRR for initial screening will always be valid. It'll always tell you if a project is acceptable or unacceptable when compared to the MAR, but it doesn't always tell you which project is best. So just to summarize again, you can't compare projects by the IRR. You have to look a little bit more closely. All right, so I'm going to give you a handout here where we've got two projects, Project A and Project B. And I'd like you to calculate the internal rate of return for each of them using Excel. And you're not going to use just the easy IRR function. I'd like you to get a little more practice calculating the IRR by iterating the unknown interest rate until you get the sum of the present worths equal to 0. Remember, that's the definition of IRR, is when the inflows and the outflows, when taken to the present, are equal to 0. So you have to try a bunch of guess I values until you finally have the sum of the present worth equal to 0. So you may have your in-class exercise paper from Wednesday of last week, and it's got kind of the template file that shows how to do that. So that's the first step, is find the IRR for both projects. And then to prove to you that IRR can't be used standalone for picking which alternative is best, I'll ask you to calculate the present worth of each of them. So we're finding the internal rate of return for each of them. And just to remind you what it looked like last time we did the internal rate of return, this was the solution from the previous in-class exercise where we had the year, the amount, and then the present worth of the amount at some I value. You add it all up, and then what you're trying to do is change that I value until the sum of the present worths is equal to 0. So that's the definition of the internal rate of return. So now apply that same method for this data set in the handout that I've just given you. So I found the internal rate of return for the first project is 12.4%. Did anybody else get that same value for the IRR? Okay. If you're having trouble remembering what the process is, then maybe you can watch me do it on project B. So I'm starting off with some guess value for the interest rate and then just typing in the known cash flow, 85,000 in expenses, then 14,000 in revenue over the course of 10 years. Find the PV of each year at this guess interest rate that I'm later going to be changing around a bunch of times. I want to find what I value makes the total go down to 0 so that there's balance between the outflows and the inflows. I can manually type that in, or I can do it in an automated way using data, what if analysis, goal seek. The goal is that the total will be equal to 0 by changing the interest rate. So of these two options, it looks like project A has the higher internal rate of return. But the question is, of the two options, which is actually the better project? Which one is going to make more money for the company? Project A or project B? So what we have to do is calculate the present worth. I've given you the factor there on the page. It says P/A factor is 8.1109. So find the present worth of each project. Okay, which project has the higher internal rate of return? Well, according to this, project B has the better internal rate of return. And just remember that we can also do it the easy way. The easy way to find the internal rate of return is just equals IRR, and then you put in the original cash flow, not the present value of the cash flow, but the original cash flow, and it'll calculate that same 12.41 that we got the long way. I just think it's important for you to understand what's happening in the background when you use a complex function like IRR. So of the two options, the internal rate of return that's the highest is for project A. So what that means is that you're earning a 12.41% return on your original investment of $50,000. But here's the thing. It's better to earn 10% on a bigger amount than to earn 12% on a smaller amount. Because project A only allows you to invest $50,000. But you're not trying to maximize some abstract interest rate. What you're trying to do is maximize the dollars that your company can receive. And so the way that we have the proof that project B is better is by looking at the present worths. So let's zoom in here on the present worth calculations. All right, so I gave you the factor of 8.1109. So that's the ratio of P to A. So if we're finding the present worth of both projects, the present worth of project A is going to be its initial cost of $50,000. And then we want to find the present worth of the revenues. And so it's $9,000 each year in revenue, and the factor here to convert an annual recurring revenue into a present worth, that's what that factor means, 8.1109. So if we combine those two things together, combining the original purchase price and the present worth of the revenues, then the present value of option A, when discounted at 4%, which is our MAR, it's $22,998. But project B gives us a higher overall profit rate. Even though it has an initial higher cost, you're also getting additional revenue each year. And so the sum of the present worths for option B is 28,553. And so of those two options, do you want to have 23,000 or do you want to have 28,000? Either one's great, but option B gives you more profit. And so the better of these options, if it's a mutually exclusive alternative, meaning that you have to pick one and you can only pick one, you can't do all the projects that are good, you just choose the best one, option B is better. Yeah.
So say you were in a situation where the project was risky and you wanted to optimize like the risk to reward with a given investment. Would a project then that had a smaller initial investment and a higher rate of return make sense to a certain extent? Just because your ability of losing on it would be smaller?
That's an interesting question. So yeah, there is a lot of uncertainty. Like in this example you've just worked, I told you what these revenues are, and you assume that yes, you are going to make $9,000 every year. But what if there was a chance that maybe you'd only make $7,000 a year? Or maybe, we don't know, or the longer you go, maybe there's more and more uncertainty. And so maybe there's something to be said for the smaller investment if there's uncertainty. But if we can be equally certain about both options, then project B is better. Are there other questions about this? Okay, so what can we use internal rate of return for? Well, we can use it for initial screening. Both of these projects are acceptable because both of them have an internal rate of return that's greater than the MAR. The MAR is 4%. Both of them have an internal rate of return that's greater than the MAR. And so project A will give you profit, and project B will give you a profit. But of the two, project B has the higher profit. And there's this question of what does the present worth represent if you're borrowing money at the minimum attractive rate of return. So remember that the MAR is set by a variety of factors, but the biggest and most important factor in what MAR you use is the weighted average cost of capital. And so how much does it cost your company to go out and raise money? You know, if you're raising it from bond sales, or if you're raising it from private investors who expect a certain rate of return, you're going to have a minimum acceptable rate of return. And the question is, when we did these hand calculations of 23,000 for option A, 28,000 for option B, like what is that amount? You can see that what I've written there is that if you're discounting at the MAR, then what it means is that this is how much profit this is the present worth of the profit that you get to keep when the loan and the interest for the loan has already been taken care of. So if we added up the total number of dollars, they're going to be a lot more than 23,000 or 28,000 in revenue. But what this represents is the present worth of those dollars that that you get to keep when the bank's already been satisfied. Okay, so any questions about the front side of the paper for comparing internal rate of return? So this would be a really good test or quiz question. We were supposed to have a quiz today, but we didn't, right? The reason why is I looked at the in-class exercise for today and I didn't think we'd have time, but I think we'll have time for Wednesday. Today was a false alarm. How many false alarms in a row could I give you?
All of them?
All of them? You're hoping?
Yeah.
So the point is that when to use these methods is almost as important as knowing how to do them, and how to interpret the results is also really important. So on this one, what it showed is that the internal rate of return can be used for initial screening. Both of these were acceptable, and beyond that, we can't choose the option that's best because project A maybe looked like it would be better because it has the higher rate of return, but it's actually project B that gives you the more profit when we look at these present worth calculations. All right, now on the back side of the paper, we're going to get some practice with the external rate of return. So I've given you a cash flow diagram, and we're going to use that same method that you first learned on Friday, where you're going to take all of the costs to the present, the revenues to the future, and you're going to do that at the external reinvestment rate. So that's the known interest rate that you do that discounting and compounding. So in this problem statement, it says that the revenue is put into an account that yields 3.5%. So that's our external reinvestment rate. So that's the known interest rate. And then the last part, where we're trying to relate the sum of the future worths to the sum of the present worths, that's where you're solving for some unknown interest rate, and you have to do it over and over iteratively. I'll bring the template suggestion up in just a moment, but I want to show you year 5. So on year 5, there's both revenue and costs. You need to find the net between them and take only the net to either the present or the future. Because if you ignore the fact that there's a revenue and a cost, and you take the revenue component to the future and the cost component to the present, then you'll get a slightly wrong answer. You'll only get the correct answer if you find the net difference between the two in year 5. Okay? So let me go back to that slide that illustrates the template method for solving external rate of return. This is how we did it last time. Okay, so remember on the external reinvestment rate, that'll be the given interest rate that the profits go to. It's the outside account where these revenues are going to be placed until the end of the study period. The study period is a 9-year time horizon, and what we want to know overall, what is the weighted average of the profits? When you take into account not only the rate at which the profits are being generated, but then the compounding effect. Like this 5,500 that you get in year 2, it's going somewhere, and this 5,500 is going to continue to accumulate additional funds until year 9. And so you're going to be earning the rate that has to do with how much is coming out of the project, and then the weighted average also takes into account that external effect as well from the external reinvestment rate. So what we should find is 17.75% interest. When you go through and do the goal seek, that is the one that makes the sum of the future value of the inflows the same magnitude as the sum of the present value of the outflows. Now you'll notice here for the outflows, by definition, outflows are negative. So I didn't put minus signs, because we already know that an outflow is the opposite direction from an inflow. And so it's only really the magnitude of these that we have to get to match when we're looking for what interest rate brings it into equilibrium.
Okay, I'm going to show briefly some beginning steps that you might consider going through as you're working on the project. And so what I've done is I've synthesized some different data. You'll notice down here at the bottom are all of the ID number datas, but I've created some special demo data that's slightly different because I didn't want to give anybody a leg up on the project by showing the actual answer. So, but the process will be basically the same. So we've got the amount, this starting savings is how much money they've got in the bank on the day that they graduate. The income the first year is the salary that they make during the first year of employment, so that's meaning from time 0 to time 1. This is their tax rate. You can see all of the expenses are shown, how much they plan to donate to charity each year, and then there's something here about how much their retirement income is going to be in today's terms. So the first thing that we want to do, I suggest, is create a column that's right here. Now, it doesn't have to be in exactly like F, but to the side of the data, and I'm going to call this the retirement income. So if they retired today at year 0, then their income would be $2,600 per month. And so that is 12 months per year times $2,600 per month. So if they retired today, then their income in retirement would be $31,200 per year. All right. And the given is that it grows at 2% per year. So that means that if they retired at the end of 1 year, then their retirement income would be the previous year's retirement income times 1.02. And now if I drag that down, every year it's going to be increasing the retirement income by 2%. Okay, so this is, I've gone all the way through age 85. Okay, so retirement income, I'm going to start another column here that is work income. Okay, now what we know about this person is that their work income is $58,500, but that is their income from working from time 0 until time 1. So they get it, because of the end of period assumption, that income comes to them at time 1 for the first year of work. So their income is going to be $58,500. I've got it at time 1 because they work from 0 till 1, then they get, let's just say, all 58,500 as a pulse. Now, how much income they make in the next year is based on this data, income growth from previous year. Okay, so the way that I'm going to calculate what their income is, if it's 8.5% higher than the previous year, then this year's income is last year's income times 1 plus this percentage. And let's just see if it seems about 8.5% higher. No, that's as a whole number. So I need to have that divided by 100. Yeah. So this is actually expressed as a whole number rather than as a decimal. So I need to have I divided by 100 to make it a percentage. But, I mean, 58,500, 8%, 8.5% more means that at the end of the second year, they get a pulse of money, like a payment for their work, and the amount they get in the second year is $63,472.50. Okay, so if I drag this equation down, then the next year it's going to be using the previous year's income plus 0.8% more. And so this trend can continue all the way down throughout time, and you see what is their work income for a given year. All right, so now I'll have income taxes, and this person, their income taxes is 14%. Okay, so it is the work income times 14%, so 0.14. So they make $58,500, their taxes $8,190. So I'm going to drag this all the way down through, and it's a flat tax. We're just, for simplicity, assuming that their income tax as a percentage stays constant over time. Of course, the amounts will change because of the income itself changing. All right, what about living expenses? Okay, just like the income hits all at once at the end of the first year, so does the living expenses. So these living expenses are all going to accumulate from living between time 0 and time 1, and then those bills are due at time 1. So I'm going to say it is the sum of these things, and you'll notice what row I'm on. I'm on the row that's associated with year 1. So this person's living expenses in the first year are $35,780. And now next year, their living expenses are 1.2% higher. So I'm going to apply that same technique that I did with the income growth. This year's living expenses are equal to last year's living expenses plus 1 plus the living expense growth divided by 100. So last year they had I wonder if this one's actually as a percentage. CA. All right, I'm just trying to remind myself because the expenses went up by such a tiny fraction. I'm not sure if it calculated it correctly. 1.2% higher. All right, I figured out my mistake. I added when I should have multiplied. All right, so let me just start from scratch. When in doubt, throw it out. All right, so this year's living expenses are last year's expenses times 1 plus the growth divided by 100. Yeah, that seems more like it should. So last year it was 35,780. This year's living expenses are 1.2% higher. And then that same formula can be dragged down through time. And some years the living expenses grow a lot, some years they grow a little. Looks like I need to make an adjustment here. Where it has the dash mark, what I mean by that is 0. So they don't grow at all. So if your data has the tick mark somewhere in the data table itself, like here's one, change that to 0. Otherwise it won't do the calculations correctly. But now mine are. And like, how do we know it's trending in the right way? Well, the living expenses look like they're never going down. Best case scenario is that it stays at 0. So sometimes the living expenses are the same in successive years, but otherwise they're always going up. And that's the way of things with inflation. All right, so we've got a column of living expenses. Now, gifts and charity. That's a constant. For purposes of our analysis, we're going to assume that this person always donates the same amount, and it is this $1,450. And I'm anchoring it with the dollar sign so that I can just drag that down through time and it stays the same. All right, so now, how much is saved this year? Amount saved this year. So the amount you saved this year is your income minus your expenses. Scenario 1 is that the person is working until age 85. So I'm not going to ever use the retirement income. They never retire in this first scenario. So like part 1, work until age 85, the amount saved is going to be work minus taxes minus living expenses minus donations. So how much is left over after covering everything else is $13,080. So that's just how much is extra in that given year. Next year, they've got extra leftovers. So you can see that every year, they've got some money additional beyond their expenses. So the last column, which is very important, investment account balance. By the way, the formulas for this is provided in the spreadsheet itself. So investment account balance. Let me make this cell a little bit wider so it doesn't break like that. All right. So for the first year, this person started off with $4,100 in their savings account at time 0. So time 0 is row 30. So this is time 0. So their investment account balance at time 0 is how much they had as their starting savings. All right. Now, after 1 year, they're going to make some interest on their investment account balance, except for here it's saying during the first 2 years assume 0 rate of return on your savings. So here, after 1 year of work, then the balance in the account is last year's balance plus the amount that you saved this year. All right? Because there's no interest that's earned during that first year. That's 0. Okay, but at the end of the second year, things are slightly different because we've got last year's balance plus how much got saved this year, plus there's going to be interest on last year's balance. So it's going to be plus 1 plus this rate of return divided by 100 times last year's balance, and that was N31. That was how much was in the bank last year. So let's just look at this formula. This is saying, you know, at the end of the second year, how much money you have in your account is the amount that you had at the end of the first year, N31, the new money that you saved this year, M32, and then this last term represents the interest that you've accumulated based on last year's balance. So this 15.8%, you get 15.8% rate of return on what you had in the bank last year, but you're not earning any interest on what you saved this year because it's just now going into the account. So it's not going to have any interest that applies. All right, so we had 17,180, then there's another approximately 17,000 going in, plus there's the 15.8% of 17,180 that goes in. So the total is $54,001.43. So now that same trend is going to continue through the rest of time. Sometimes it's going up, sometimes it's going down, because like we'll see this in the next year is a negative rate of return. So we're still saving money, and we still had an investment account balance that was positive, but some of our savings are going to decrease because of that negative value there. So let's see. We've got in this cell $54,000 plus 16,700 approximately, and then we've got a decrease. All right, I just noticed a mistake on my formula. This is what happens when there's no no net. All right, so starting here, it should just be that. So let's just manually check. Let me delete this. Let's manually check this. Like we know that it should be 17,180 plus we're also going to add 16,926 and 99 cents, and then there's also going to be 15.8% of the previous year's balance, so it's that. So 0.158 times this balance. So now we need to add these three things together. So the sum of those three things, 36,821. All right, good. So it's settled now. So let me show you again. Let me talk you through. So the investment account balance at the end of the second year is the investment account balance at the end of the first year plus the amount that was saved during the second year plus the interest on the previous year's balance. And so my mistake here was that I was doing 1 plus I. It should just be I times the previous year's balance. All right. So now we can see the investment account balance varying over time. And so if this person works until age 85, so here's the age, works until age 85, then their investment account balance would be $5.8 million. Of course, this is a simplification because the reality is when people start making more money, they start spending more money. Inevitably, if you were content to live in a one-bedroom apartment when you first graduated from school, once you start getting extra money, you may have to economize a little bit. Okay, I just got interrupted by a phone call. Sorry about that, but hopefully the point is clear about how to solve part one. Basically, you're just trying to find out what is the investment account balance at the end of 85 years if that person works. I'm sorry, at age 85 if that person works the whole time. Part two is work until age 67 and then retire. So there's a transition, and the question is what happens to their income during those years. And so if they are working all of that time and then they retire, basically we could copy over some of the same stuff, like there's still going to be the same work income, the same income taxes. Let's just actually here have a column that's titled income, work or retirement. Okay, so their income transitions at age 67. So it is the work income through age 67. So age 67 is, in this case, row 72 right here. So what I'm going to do is they work until 67. So at row 72, I'm going to have it switch over. So watch for the income column. It starts off just going with the work income, and then when I get down to row 72 is the last year of their income from work, and then after that, now their income is this retirement income, which was this one. So remember that there was this column, like if they retire in a certain year, how much they get in that year for being retired. Okay, so then it continues onward until age 85. So they have a decrease in their income when they do that retirement. The income taxes, we're going to assume always stay at the, what was it, 14%? Yeah, 14%. 0.14 times this. All right, so we've got the income taxes, which have a sudden decrease when they stop working, and the income goes from the working wages to the retirement wages once they're drawing the pension. Living expenses are going to be the same, gifts and charity is going to be the same, but you'll have a different amount saved this year and different investment account balance. The question is, we just want to look at how does the investment account balance change over time if they do that working until age 67. Now, if we just look at the other scenarios, at what person can the age stop working and die with zero at age 85? So what that means is that in the third scenario, rather than having the transition, like we did this transition in part 2, basically the idea in part 2 is transition from work income to retirement income at age 67 and see what is the investment account balance over time. That's the essence of part 2. When you get to part 3, you're going to not have it transition at age 67, but see, like, could you transition at age 66? Could you transition at age 65? And you're going to be having calculated the investment account balance. So, you will have calculated all of these other columns as well. And we want to know, like, when the person dies in their final year, can you get that investment account balance down to 0 or close to it by optimizing when they retire? Like, could you have that person retire at age 60? So age 60 is row 65. So if you had that transition from work income to retirement income, if you do that at age 65, then how does your investment account balance look when the person is 85 years old? So the essence of the scenario 3 is just how early can you have that person retire. Scenario 4 is they're working until age 67, so that's like a duplicate of scenario 2, but now what you're doing is you're increasing the amount that they donate each year. So instead of donating this fixed $14.50, you're going to be doing a goal seek to try and see, like, what is the goal seek gifts and charity amount that will have them so that they have 0 investment account balance at the end of 85 years. And then the final scenario that you're going to be looking at here, develop your own plan. That's where you personalize it yourself. You decide how much to give to charity, how early to retire, play with all the controls and see what plan you're going to do in order to die with 0 at age 85. All right, so hopefully that little illustration was helpful and gave you an idea of where to begin. And as you're working on the spreadsheet, feel free to stop by my office if you want some assistance. I'd be happy to help you if you stop by during my office hours.